Okay, this is video number 4 on SPSS. Let's start. We will start talking about paired and not paired data. Okay, there's a big difference between couples of data. Even when you have two sets of data, the data may not necessarily be paired. So here we are talking about a situation in which you have two sets of data, of scale data. Okay. There are two possibilities. The first one, your data are not paired. For example, sex and number of exams. You have a set of number of exams for male and another set of number of exams for female. In this case, the data are not paired. Paired means coupled. So there is not a correspondence in each number of exams in your set male with a corresponding number of exams in your set female. So the two groups are totally independent and not paired. Another example, different, may be the grade student receive in the exam of mathematics A and the grade student receive in the exam of mathematics B. In this case, the data are paired. It means that even though you have two different sets of grade, the grade for mathematics A and the grade for mathematics B, there is a perfect correspondence. So there is a student, John Smith, which has a grade in the first set, and the same student which has a grade in the second set. So this is the big difference between paired and unpaired data. In SPSS, you easily recognize this data because paired data use two different variables, and there is one value for each person in each variable, so a total of two values for each person. Not paired data use instead one numerical variable and one nominal variable. Okay, so you will find one scale value for each person and stop. Okay, now we will see some analysis techniques for scale versus scale. All these techniques talk about paired data. So in all these cases, the two scale variables are paired. So we have two values for each person, one for the first variable and another one for the second variable. Okay. You can imagine, for example, the grade received in mathematics A and the grade received in mathematics B, okay, or some other data. Let's open here the file coupled data. This file contains two scale variables which are coupled. You can imagine that the cases are shops. So 1, 2, 3, 4, 5 are different shops, and this is the amount of product A and the amount of product B sold this year in each shop. So this shop sold 72 product A and 15 product B. It's a very small shop. This one is very large and sold 18,000 product A and 20,000 product B. Okay. We will compare these two series to check whether there is a relation between product A and product B. Okay. Let's see. Okay. Pearson and Spearman correlation. Spearman correlation. You should be familiar with Pearson correlation. It's called linear correlation coefficient. It's the most famous measure of relation between two series. Spearman correlation is the same thing, but from a slightly different point of view. It's the non-parametric version. Okay, let's see how to calculate them. Okay. They check whether there is a correlation between the two series. Analyze, correlate, bivariate. Okay. You put the two variables involved. Oops. Okay. You can check for Pearson correlation and for Spearman correlation at the same time. Please, at the exam, if I ask Pearson, only Pearson. If I ask Spearman, only Spearman. Okay, don't check both just because they are here. Okay, what's the meaning of this correlation coefficient? Well, it's very famous. If it is equal to 1, it means that the two series are almost identical. If it is equal to -1, the two series are perfectly negatively correlated, so they go in radical opposite direction. If it is close to 0, it means that there is no relation between the two series. Okay? Correlation, this is the Pearson correlation. You can see that SPSS produces this strange matrix. Well, when the variables are only 2, it's really nonsense. The only meaningful number is this one. 0.85. It means that the two products are strongly correlated, so it means in this case that when one number is large here, it will be large also here. And when one number is small here, it will be small also here. Okay? 0.851 is the result. This Spearman correlation, Spearman law, it's very similar. You can see also the result, 0.893. Okay. And these are Pearson and Spearman. Okay. Now, to test, we check whether there is a linear correlation for Pearson and a correlation for Spearman between the two variables. Correlation is 0. And significance rejected, so the correlation is clearly not 0, as you can see here, 0.9893. So it's very far away from 0. Okay. Let's see a slightly different, before going to a slightly different thing, let's see how you can analyze several variables at the same time. Sometimes you have 50 scale variables, and you want to analyze all 50s, all couples among these 50 variables. So the first with the second, the first with the third, the first with the fifth, up to the first with the 50s, and so on. So when the variables are several, like for example, let's do it here. Let's analyze year of submission, year of birth, first year of elementary school, number of passed exams, and how many days a week do you come here during exam month. Let's ask only for Pearson correlation. So if you put more than 2 variables, SPSS will analyze the correlation between the first and the second, the first and the third, the first and the fourth, the first and the fifth, the second with the third, the second with the fourth. So all the possible combination 2 by 2. Okay, so in this case, SPSS will not analyze the correlation between among the 5 variables. It doesn't make sense. The correlation is always between 2 variables. Okay. You can see the result. Okay, so here you have the correlation between year of submission and year of birth, the correlation between year of submission and first year of elementary school, between year of submission and passed exams. Okay. Obviously, there is a strong correlation between year of birth and first year of elementary school. Well, this is obvious. Okay. Also, there is a slight correlation between year of submission and year of birth. Okay. So, you can see the result is always this matrix, so you can analyze the correlation among several couples of variables at the same time without having to do all the couples one by one. Okay? So I repeat, this is not the correlation between among these 5 variables, it's the correlation between couples of variables. Obviously, year of submission with year of submission, since it's the same variable, the correlation is 1. Perfect. Okay. There are, however, situations where this correlation can be influenced by a third variable, okay, which completely screws up the correlation. I have this famous example depicted here. This bird is I think it's a straw, the name in English, and some people claim that it carries children. Okay. In fact, if you do a statistical analysis, you take the land by land or zone by zone, you take the amount of straw present and the amount of newborn children present, you see that there is a significant positive correlation between these two variables. So there is a positive correlation between the amount of straw present and the amount of children present. This is rather strange, okay, because we know that it's not true that straw carry children. So apparently, let's try to... Apparently you experience a positive correlation. Let's indicate a positive correlation this way, with the symbol plus here, between these two variables. Okay. So we could claim that either the presence of straw increases the number of children, or the presence of children increases the number of straw. It's rather strange. So there is a statistical correlation between these two variables. Well, it has been shown instead that this statistical correlation is not direct, but it's, let's see, how do we call it? Spurious. Okay. It means that there is a third variable, let's call it type of zone, or urban. The type of zone, whether it's a rural area, so in the countryside, or an urban area, so inside the town, which influences both not this one. Influences both variables. Okay. So if it is a rural area, it will increase the presence of straw because it's a natural environment, and will increase the presence of children due to social reasons. If it is an urban area, it will decrease the presence of straw and decrease the presence of children for social reasons. So there is not a really direct relation between these two variables, even though there is a statistical correlation, but the relation is through a third variable, the type of zone. So there are many situations like this when you do a statistical analysis, so you can discover a correlation between two variables and be misled and believe that there is a real relation between the two variables, while it's only a spurious relation. It's made up by a third variable. Okay. So many times you want to check the correlation between two variables, controlling for a third variable. It means that you keep a third variable under control, so you remove these two effects, and you want to check whether there is a relation between two variables. Okay. In SPSS, it's possible to do this thing here. So it's possible to check the correlation between two variables, only the Pearson one, controlling for a third variable. Let's, for example, here check whether the relation between year of submission and year of birth, there is a correlation. You can, where is it? Pearson only. There is a correlation of 0.116, whether this relation is spuriously influenced by the variable, for example, sex. So in order to check it, we use partial. You can see the picture 1, 2, -3. It means that you check the relation between 1, 2, keeping third variable under control. So year of submission, year of birth, controlling for sex. Okay. It means that you remove the effect of sex on year of birth and year of submission, and then you check the correlation. Everything is done automatically by SPSS. Okay. And you get a new correlation which is lower, 0.096. So it means that sex played a slightly active role between these two, this relation. Okay. Let's do the same between year of birth and first year of elementary school, which display a very large correlation. First year of elementary school, controlling for sex. Okay, the correlation remains large. It means that sex didn't play any active role in influencing this correlation. So, this is the case when you suspect that there is a third variable influencing the relation and you want to remove its effect. Okay. A student test for pair data. This is very similar. It's here. It's still a parametric test. Okay. However, instead of checking whether there is a correlation such as when one goes up, the other one goes up, when one goes down, the other one goes down, it checks instead whether the expected value of variable 1 is equal, or better, there is a fixed difference with the expected value of variable 2. So it checks whether the difference in the expected value is fixed equal to m. Unfortunately, as you can see here, SPSS is able to do the test only for m equal to 0. So SPSS will simply check whether the expected value of the first variable is equal to the expected value of the second variable. So we'll check whether, on average, the two variables are the same. Officially, in statistics, you can do this test even with an m different from 0. So you can check whether there is a systematic difference between the two expected values. In SPSS, you can do it only for m equal to 0. Okay. Let's take this couple data and check whether there is a systematic difference or not between these two variables. So we check whether the expected value of product A is equal to the expected value of product B. You can immediately see that the result will be reject, because it's evident that product A is almost always larger, for example, here, especially for low values, here, than product B. Let's see, however, whether this, my first preliminary impression, is correct or not. Analyze, compare means, paired sample t-test. So now we do the last student t-test, the one for paired samples. You can see also the little pictures. Here it was A minus B, so group A minus group B. This is A1 minus AB, so coupled. A1 minus AB, A1 minus AB. Product A is first variable, product B is second variable. Okay, so you can see here it's very clear that the variables are coupled. Okay. You can do other couple of variables. In this case, SPSS will produce one test for each couple, so not all together, we'll produce one test for each couple. Okay. And the result should be here. Here, let's see all this chaos. The average of product A is 8,000, of product B is almost 10,000. So it was not true, my impression. Product B is larger. The difference product A minus product B has an average of minus 1975. Significance 0.02, so you reject. Okay? It means that it's not true that the two expected values are the same. In fact, you can see they are very far away. Okay. Let's see some exercises. We have already done the first. Let's see, is there a relation between sex and the preferred exams? Well, it's very easy to do this exercise because you just look at the variable types. Sex is nominal, 2 values. Preferred exams is nominal, 5 values, I think, or 6. Well, in any case, 2 nominal variables, 2-dimensional contingency table to get a description, and a test chi-square. So, analyze descriptive statistic cross tabs, sex, or his favorite subject. If you want, you can get immediately the test. The exercise which are in the slides are loose exercise. I mean, I'm not very precise. I just give you a hint, and you do more or less what you want. Int exam, obviously, since I have to give you a grade, I will be very precise on what you should do and what you should not do. Okay, so this is the table. Okay. It will be better to display also the raw percentage to have a better overview. However, the chi-square test tells us that the difference is not significant. We have here to accept, okay, 6%. Let's do the others, the other exercises. Universities and apartment mates grades. So I want to check here whether there is a relation between the grade you give to university and the grade you give to your apartment mates. There are many people which, when they have to give a grade, are very pessimistic and they always give low grades. On the other hand, there are optimistic people, enthusiastic people, which always give positive grades. Okay. Let's see whether there is really a relation between the grade given to university and the grade given to apartment mates. These two are ordinal variables. You could say that there are nominal variables and perform the chi-square with a cross table, or you could claim that there are scale variables and perform one of the many other tests that we see for scale variable, the Pearson, the Spearman, and the student test for paired data. Let's suppose that there are scale variables. We start with the correlation, reset, so between university grade and think of apartment mate. Let's ask both Pearson and Spearman. Pearson minus 0.173, it means that if you give a large grade to university, you will give a bad grade to your apartment mates. Also Spearman confirms, even though it's all very close to 0. Let's do a student test. You can see that student test more or less checks the same thing, okay? But it's not exactly the same. It works on expected value and not on the series in general. Okay. Student test. University grade. Think of apartment mates. Well, university grade has an average of 3.54, apartment mates 3.73, so people tend to give a larger grade to apartment mates. There is not a significant difference. So it says that the averages are more or less the same. Passed exams and year of birth. Okay. In this case here, you check whether older people have more or less passed exams. They are both scale variables, so the tests that you should do are obvious, Pearson and Spearman, or student test. We start with Pearson and Spearman. Year of birth and passed exams. 0.117, 0.026. In both cases, you get not significance. Let's do the student test, reset, passed exams, and year of birth. 0.000, so instead, student test gives us a different idea. The expected value, no, pay attention, the expected value of year of birth is very different from the expected value of passed exams. Okay. Is this in contradiction with the previous result? Here they say that year of birth and passed exams, well, slightly move in the same direction, but not significantly. Okay. So when year of birth increases, passed exams tend to increase, so younger people tend to have more passed exams. But it is not significant. Here instead it says that there is a significant difference between the average of passed exams and the average of year of birth. Okay. Are these results in contradiction? Well, no, because they show completely different things. Look here. It's evident that the average of year of birth and the average of passed exams are different because they measure something which is totally different. This one measures years and this one measures exams. Okay. So this test really, from a statistical point of view, is totally meaningless. How can you compare the average of passed exam with the average of year of birth? On the other hand, this test is, from a statistical point of view, is the right one. Okay. You check whether when one increases, the other one increases. Okay. So even though they are in the same variable set, they measure two completely different things. This one measures the difference in the expected values, which sometimes may be meaningful, other times may be meaningless. And this one checks whether when one increases, the other one increases. The degree and living with other students. Well, degree, it's nominal, 6 values. Living with other students, nominal, 2 values. So it's evident, cross-nominal, 2 values. Practicing one sport is nominal, 2 values. So we analyze whether practicing one sport improves the chances of passing decision theory, or vice versa, if having passed decision theory sends you to practice one sport. It's clearly cross-tabulation with Pearson chi-square. Okay. We'll do, however, all of the sports together. Let's see how. Reset. Decision theory here. And the sports here. This does not mean that we will build a big table with decision theory and all the others. We will build instead 6 or 7 tables with decision theory running, decision theory swimming, decision theory diving, decision theory skiing, etc., etc., etc. Statistic square. And I would add also the raw percentages. Okay, let's see the result. First table is only a summary table, you may skip it. Here, you can see from here, people who pass decision theory perform less running, so only 48% run, and 51% don't run. Okay. So there may be a significant difference. So the more you run, the less chances you have of passing decision theory. Well, it's almost significant. I know, this one. 10%, I would not say significant. Swimming, it is absolutely not significant. Diving, absolutely not significant. Skiing, it's evident from the table that it's not significant. 75-24, 77-22, in fact. Football, also evident from the table that is not significant. Basketball, evident from the table that is not significant. Volleyball, evident from the table that is not significant. So the only one which is slightly significant is with running, okay, which seems that, however, it's 10.5%, so it's not very significant, that the more you run, the less you pass decision theory. Okay. Let's do some more interesting. Here, passed exams and days spent here during exams. You may claim that the more time you spend here during the exams, the more exams have you passed. Let's see. We use a correlation, bivariate, reset, passed exams, and how many days a week do you come here? Pearson and Spearman. Very slight correlation, 0.012. Spearman becomes even negative. It means that the more time you pass here, the less exam you pass. The more time you spend here, the less exam you pass. Okay, Spearman is more or less the same, but from a slightly different point of view. Okay. Now, however, before going on, is it meaningful here to perform also student t-test for coupled data? Let's do it and see whether it's meaningful to do it. Usually you should know it before, but reset, passed exams, how many days a week. Well, look, you see that the average of passed exams is 23. The average of how many days a week is 4.2. Well, clearly these two things are different, but they're different because they measure completely different things. So this is another example where it's totally meaningless to do student t-test for pair data. So you will do student t-test for pair data only when the two data represent the same thing, like grade in mathematics A and grade in mathematics B, or year of birth, year of elementary school. Not when the two things represent completely different things, which obviously have different averages. Okay, let's do this one. Passed exams and days spent here during exams, controlling for year of birth. Okay, this time I suspect that there is no relation between passed exams and days spent here during exams, because year of birth plays a reverse role, so it influences positively one variable and negatively another one. It may be possible. Let's see whether controlling for year of birth, so keeping year of birth under control, are we able to show a relation between passed exams and days spent here during exams or not? So we have seen how to do before. Reset. Year of birth, controlling for passed exams, and how many days a week. So the controlling for variable may be either numerical or nominal, so scale or nominal. You can put both here. While variable here must be scale, or at least ordinal. Okay, the relation now here is totally zero. So if you remove the effect of year of birth, there is a perfect not relation between the two variables. Okay, now we will switch to charts. SPSS has a lot of charts which you can use. Obviously, the chart to use depends on the variable type, as you can see here and here. So not all the charts are adapted for all the variable types. Let's make an overview on the charts. Charts in SPSS are here. They have the chart builder. If you like to use the previous charts, it's okay, they are here. Chart builder, however, it's more interactive. Okay, first of all, choose the variables. So let's start with the first easy one, the bar plot and the pie chart. So this for nominal variable, let's take favorite subject, for example, and choose the bar plot, this one. You drag favorite subject here, okay, and you get immediately an overview. The overview is usually correct, but don't rely on it. Click instead OK, and you will see the bar chart. Okay, pie chart, it's identical, but rather technically identical, but graphically completely different. Pie. Okay, drag favorite subject here if it is not displayed. You can see here that you always have a count, because each slide corresponds to count. Well, percentage value sum are rarely used, it's much better to use count. Okay, you can see here the famous pie chart. This graph can be changed from an aesthetical point of view. You just double click. Okay, and the chart editor appears. What can you change here? Well, really a lot of things. You just click on one element, or better double click, and this property bar appears, where you can change many things. For example, fill and border. Apply, and you can see all the bars have changed color. Okay, you can change the background, so just double click on the background, make the background green. What is very famous and very similar to Excel, you can change the scale here. You just click here, text style just to change the text, or scale. For example, you want to go from 5 to 45 with steps of 5. Okay, apply, and you will change it. Okay. For bar charts, you may want to change this one. For example, here none is really meaningless, so you want to remove it maybe. So you go to categories, you click on none, and you remove it. Okay. Apply. You can see now none is not. You want maybe to put economics at the beginning, so you select economics and you move it at the beginning. So you can do also many changes here. When you have done, remember, file close. It's the best and the safest solution. If you do something else, I don't assure you it will work. Okay, you can see everything perfect. You can change also the font and do a lot of other aesthetical changes. Okay. But what is interesting is that when you are satisfied with how your graph look, typically you would like to use the same graph style in all the other graphs that you have in your thesis or in your book. Okay? You don't want each graph to look differently. It's really odd. And you don't want for each graph to manually change it. So you will save your graph template. Okay, so double click, file, save chart template. Okay. You can decide what to save, the layout, the chart size, the orientation, the X, the Y axis, and blah, 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 blah. You can save all settings, but in this case, you will save also the title of the axis. Many times you don't want this title to be saved. So decide yourself which template you want to save, which parts of your template you want to save. Give a brief description and you can save it. Okay. Blah, blah, blah. Your template name and save. You can also apply some predetermined templates. So I have the blah, blah, blah. But if you search through your folders, you will find SPSS already predefined templates. Okay. Okay, let's see if there is something else which may be interesting. No, not this one. Oh, let's remove. Here, show data labels. Display the data labels. Okay. You may decide what to show. Maybe the percentage is better than the count. Apply, and you see the percentages. You can put them, for example, here. So there are really a lot of things which you may want to do. File, close. Same thing here. Okay, identical. You can also move one slice out, all the slides out in this case. There is no way to move only a single slide out. No, or either all of them or none of them. You may want to display or not display the legend. Okay. You may want to change colors or change the color even of one slice only. Okay. You may want to make it three-dimensional. So there are many changes. I think you have all the possibilities here. It's very easy to use, and especially you just click on the items and it will show you the appropriate menu. Okay, also here you can remove category none. Okay. File, close. Let's see other examples of graph types. The histogram, a very famous graph type in statistics. The histogram is used only for scale variable. Let's build the histogram of year of birth. Please, histogram looks like a bar plot, but the bar plot is for nominal variable, the histogram for scale variable. Do not build a bar plot for scale variable or an histogram for nominal variable. It will be marked obviously as an error. Okay. this the histogram? Well, in this case, since there is somebody who says to be born very early, it doesn't make too much sense, so let's restrict it. Scale 19, I will say 55, 1955, to 1995, major increment 5, apply. Oh, now it looks much better. There is one thing in histogram which you may want to change, which may completely change the graphical representation of the histogram, and it's the binning. So it's the how large these intervals are. In this case, you can see intervals are 5 years large. You can make them of different width. Just double click on the bars, choose binning, this is very important. Instead of automatic, use custom. You can decide to make them 3 wide. Okay. You can see here the intervals will be smaller or even 2 wide. Okay, much smaller. Or even larger, 7. Okay. The histogram will change completely. You can design instead the number of intervals, 10. 20. Okay. Don't ask me why Excel, but SPSS converts it to 0. SPSS has some little interpretation problems. Large 5. Let's leave with 5. Okay. Okay, according to what you choose as a binning, it will change completely your histogram, as you have seen. Okay, so what is this? Okay, another thing you can show above an histogram is the normal distribution curve. Please do not display it in histogram unless it's specifically required. There is only one case where it's specifically required. We'll see it later. Okay. So usually do not display it. Now how can I remove it? Pressing Enter. Clicking on it and press. Remove items. No. Clicking. Press Enter. No, it cannot remove it anymore. I have to redo the histogram in this case. Okay, let's see other types of graph. Another type of graph for one scale variable, it's the box plot. It's not so famous as the histogram. Let's see it. Let's keep always year of birth, box plot. This one, please the last one. The last one is for one variable only. The other one will be discussed later. What does it show? Well, the black horizontal line is the median. The orange rectangular, it's the central 50% of the data. This thing here represents other things such as the 90% of the data. And this here are the outliers. So all those people which are strange. In particular, you can see this person 195, is very strange. Okay. So you can decide to remove it from the data, for example. Okay. It also displays you who is the strangest. Okay. Also here you can do a lot of modification, just double clicking, opening the chart editor. You double click again. You can decide, for example, that the median be red. Okay, so you see it very well. You can decide that the box be much larger. Okay. You can decide to suppress these numbers here, just pressing Enter. Okay, you just see the symbol for the outliers and not the numbers. You can decide to change the scale, obviously, as usual, 1955. Okay. Now it looks much better. Now you can clearly see that the median is 1986, and the central 5% lies between 1985 and I would say probably 90. Okay. File, close. It's a graphical representation of one scale variable. It's completely different with respect to this one, but it's still valid because it tells you how the distribution is done. Okay, last graph, let's switch to two variable graphs. You can easily copy the graph with copy and paste it inside Word. Okay, pay attention, however, that once the graph is inside Word, let's make the example. For Word, this graph now is just an image. So you cannot edit anymore, you cannot change the scale anymore, you cannot do anything, it's an image. So if you copy and paste the graph, once inside Word, it's an image. So I strongly suggest you to do inside SPSS all the aesthetical modifications. Because once it's copied inside Word, you cannot do anything. Okay. Especially, please enlarge these numbers here. Many times I see in your thesis that these numbers are really invisible. Make them very large. So once you copy and paste it inside Word, okay, if you reduce it, the numbers will still be readable, and also year of birth should be enlarged here. You can see, moreover, that SPSS very kindly does not display birth, but year of birth, so the label. This is the reason why I told you it's very important to put the labels correctly, because you will have them displayed in your output and in your graph without any extra effort. Otherwise, you have to manually correct it every time. Okay, let's switch to graphs for two variables. We have seen until now the bar plot, pie chart, histogram, and box plot. When you have two variables, you can still do the bar plot for a nominal and another nominal. For example, this one, obviously, not this one anymore, but this one. So sex, you put it here. It means that sex will force you to change color, and here favorite subject. Okay. You can see the comparison statistics is very similar. Computer science unbalanced towards male. It would be a good idea to move female, convert female to pink traditionally. At least this, which seems okay. Now it's clear who is who. Okay. You can also switch the two things, so make male and female here and the favorite subject here, but it will be totally unreadable. That's it. So you put sex here and favorite subject here. You can see it works, but it's totally unreadable. The box plot, it's a very good tool to compare two scale variable with a binary nominal. Okay, let's see how to do it. For example, the distribution of passed exams by sex. No, sorry, this one, sex here, it's okay, and passed exam here. So, in the box plot, the scale variable is always on the vertical axis. Okay. In case you have a nominal variable on the horizontal axis, always don't make the opposite. First of all, SPSS will not let you do, but you will not have the result that you want. Okay, you can see. You can see here that the distribution for male is slightly moved upwards, but with a lot of outliers here. Okay. Obviously, if you restrict the scale for passed exams, it will look better. Okay. Double click. You can also twist the graph, make it horizontal. Let's see if I am able to do it. No, it doesn't seem. Data label more. transpose chart coordinate system. So in this direction, which maybe in this case is better because you can compare the medians better. Okay. And finally, the famous scatter plot. The scatter plot can be done only with two coupled scale variables. Okay. So for example, year of birth and first year of elementary school. Graph chart builder. Scatter. Year of birth and here first year of elementary school. Oops, too many variables. Reset. Scatter. Year of birth and first year of elementary school. Okay, you can see there is a linear relationship very clearly. Again, we have the usual person here. Let's remove it. Remove, at least do not display him. Okay, and also here. Okay, you can see here the relation is almost linear, okay, with some people going to school too late or too early. Okay, you can change also the symbol. If you don't like you can put the triangle, filled maybe. So let's fill it with red. Okay, a red triangle with a blue border. Let's make it larger. Okay. So you can choose your favorite picture. Okay, and this is the famous scatter plot. In the scatter plot, as you probably know, you can draw the regression line. This is the famous regression line. We'll see, however, also later how to do it, but just click here. This is the regression line. In this case, you can see the data are exactly on the regression line, which is really wonderful. Okay. There are many regression lines which you can want. Let's make another example of scatter plot, passed exams and year of birth. Year of birth here and passed exams. First of all, let's remove this one and passed exams. You can see this two instead. Again, we have the same smart person who was born in 19. Okay. You can see here there is evidently no linear relationship. Even if you draw a line, okay, the line is almost horizontal. Okay, it doesn't help you too much. You have the R squared, a very famous statistical measure. Okay, finally I want to show you an effect. What happens if you draw a scatter plot with an ordinal variable, or in any case with a variable which has few values? For example, passed exams still here, but put university grade here. This is what happens. Okay, so even though ordinal variable can sometimes be considered a scale variable, pay attention when they have few values, because you have this horrible effect, and the scatter plot really now doesn't mean anything. You have all the values accumulated here. Okay. In case like this, it will be much better to put a box plot, such as this one. Where is the box plot? With university grade here. Because it is much more meaningful than this one. You can see here the medians where they are and the distribution where they are. Okay. As a homework, I suggest you to do all this graph. Make your graph look as similar as possible to the picture. In some cases, it may be impossible for you to make it exactly identical because they have been built with several different versions of SPSS. But what is important is do exactly what's indicated here. So this is your major task. So make it look as you see, but your major task is to do this thing here. Okay, you can see this also involves 2 nominal variable and 1 scale variable. Okay. The result also will be, from a numerical point of view, different, because this data were the data of 2 years ago, and now you have more data. Okay. However, you can see there are all graphs that you can easily build. This is a scatter plot, for example. Okay.